Welcome to Momentum, Impulse, and Collisions Problem Set Solvers. Before we get into how to solve the problems, let's take a look at the equations that are going to help us out. For momentum, we're going to use momentum is equal to mass times velocity. That's our inertia on the move or mass in motion. In order to figure out impulse, we need to remember that impulse really is just a change in momentum. Now, it is very rare that mass is going to be what is changing. So it is far more likely that what we will actually see is that velocity changing. So all the same, it's our change in momentum which requires us to have a force applied along a given time. Now, in order for us to figure out collisions, we need to go back to Newton's second and third laws of motion. So, a force, for every action there is an equal and opposite reaction. And we know from Newton's second law that these forces come from masses and accelerations. Now, acceleration is really simply just a change in velocity over time. So we can say that our forces, equal and opposite, are really looking at mass and how velocity is changing over time. Now if we look at that, we see our momentum equation buried in here, and we recognize that our change in momentum is equal to our force multiplied by time, and that in a collision due to Newton's second and third laws of motion, that these forces are going to be acting in an equal and opposite way. Now, when we are talking about the change in momentum, we can really look at how momentum is changing. In an elastic collision, our momentum before the collision is going to be equal to our final momentum after the collision. In an inelastic collision, the momentum before the collision is going to be equal to the total mass and the final velocity. Let's go ahead and apply some of these and see if we can't help make them make more sense. So, first of all, how do you find momentum? Let's take a look and see if we can figure out the momentum of a 60-kilogram halfback moving at 9 meters per second. First of all, what do we know? We know his mass is 60 kilograms. We know his velocity is 9 meters per second. We've been asked to find momentum. Momentum is mass times velocity. Do we have enough information to do this? Yes, we do. We know a mass, which is 60 kilograms. We know a velocity, which is 9 meters per second. So simply multiplying those together will give me my answer of 540 kilogram meters per second. Let's try one more. What about finding the momentum of a 1,000 kilogram car traveling northward at 20 meters per second? So our mass is 1,000 kilograms. Our velocity is 20 meters per second north. We've been asked to find the momentum. We know that momentum is equal to mass times velocity. Do we have enough information to solve this equation? We sure do. We have 1,000 kilograms multiplied by 20 meters per second gives us an answer of 20,000 kilogram meters per second. Before we move on, let's do a couple of really quick conceptual ideas. If a car actually has a momentum of 20,000 units, what would happen to that car if we doubled the velocity? Let's take a look. We know that momentum is equal to mass times velocity. If we doubled the velocity, what would have to happen to our momentum? Yes, it too would have to double. What about if we had to triple it? With taking a look at our equation, what we do to one side, we have to do to the other. So it would also triple our momentum. What would happen if we doubled the mass? Then once again, our momentum doubles. Let's see how impulse plays a part. Let's say that we have a friend Jennifer who has a mass of 50 kilograms. She's traveling at a velocity of 35 meters per second in her red sports car when she must suddenly slam on the brakes to avoid hitting a deer or crossing the road. As she hits the brakes hard, she strikes the airbag and comes to a complete stop in 0.5 seconds. What we need to know is what is the average force acting on her as her face and body reach the safety equipment, the seatbelt and the airbag. Well, this is one where we have to think about what's going on before we start trying to plug numbers in. So we know that the impulse is equal to the change in momentum. So that's another way of saying our mass times our change in velocity. Now we know that our velocity went from 35 meters per second down to 0 meters per second. So the change that Jennifer experienced was 35 meters per second. Now as we look at this, we just need to find the force. So what we might want to do is solve it symbolically first. This will cause these times to cancel out. So force is going to be equal to our mass, which is 50 kilograms, multiplied by our change in velocity, 35 meters per second, and divided by 0.5 seconds. This will give us an answer of 3,500 newtons. Now what if Jennifer forgot to put on her seatbelt? She still has a mass of 50 kilograms. She's still traveling at a speed of 35 meters per second. But this time, her face is going to make a connection that's much harder with the windshield, and it's going to happen in 0.001 seconds. So once again, we want to find what the average force is. So once again, we're going to take a look at our impulse, which is equal to our change in momentum. We're going to divide both sides by t and realize that our force is going to be equal to our mass times our change in velocity divided by time. Do we have enough information to solve this problem? 50 kilograms times by 35 meters per second divided by 0.001 seconds. So what is this going to do to the average force? The force is going to increase to being 875,000 newtons. Let's take a look at how we can use this information to solve a problem where we have two objects interacting. One day, we have a fish that happens to have a mass of 5 kilograms swimming along at a rate of 1 meter per second. It spies ahead of it a rather thoughtless fish sitting at rest with a mass of 1 kilogram. What we want to know, what will the speed of our bigger fish be after lunch? So what do we know? We know that mass 1 is equal to 5 kilograms. That's talking about our fish here. We know that our velocity 1 is equal to 1 meter per second. We know that our second mass is equal to 1 kilogram. But our velocity 2 is equal to 0 because our fish himself is not moving. Now this is another one where we need to think about what is happening. Is this an elastic or inelastic collision? Well, in an elastic collision, the two fish would bounce off each other. Since in this particular case the bigger fish is going to make the little fish lunch, I would say this is an inelastic equation. So we've been asked to figure out the final velocity. So we're going to take a look at the fact that our momentum before the collision is going to be equal to our final momentum. And our final momentum includes our total mass and velocity. So m1v1 plus m2v2 is going to be equal to our mass total and our final velocity. So let's go ahead and see how this looks in calculation form. So 5 kilograms times by 1 meter per second plus 1 kilogram times by 0. Let's go ahead and solve it that far. So 5 plus 0 gives us 5 kilogram meters per second. So we know that 5 kilogram meters per second is going to be equal to our total mass multiplied by our final velocity. So what would our total mass be? Well, our mass total is going to be m1 plus m2. In this particular case, 5 kilogram plus 1 kilogram lunch. So a total of 6 kilograms. Divide both sides, and we end up with our final force is equal to 5/6 newtons. Actually, I meant our final velocity is equal to 5/6 meters per second. Thanks. See you in class.